Okay, so we are doing exponential growth and decay. So exponential growth is when a quantity increases by the same factor over equal amounts of time. The standard form of this type of function is y equals a times 1 plus r to the t power, where a is my initial amount, and it's greater than 0. R is the rate as a decimal, so this means divide by 100. And t is my length of time. Okay, so it says the population of Hillville grows at an annual rate of 15%. What will the estimated population be in 5 years? So, my rate is 15. I want to divide that by 100. And what is 15 divided by 100 as a decimal? 0.15. What's the length of time in the problem?
5 years.
And the population is my initial amount. This is coming from the picture it gives me. How much is my initial amount? 5,000. So then I want to go ahead and plug this all into my formula. So I'm going to have y equals, instead of a, I'm going to have 5,000. And then 1 comes from the formula. Plus is coming from the formula. My r was 0.15. Then I have an exponent of 5 because that is my time. And then if you guys didn't grab a calculator, I'd go grab one right now. There should be lots of people getting up. Not very many of you have calculators on your desk. Okay, so then I want to go ahead and type this into my calculator. So I'm going to type 5,000, parentheses 1 plus 0.15. Oops, that's kind of... Then, to get my exponent, that's above the divide symbol. So this button right here. And then I type in my, 5. Okay, and then my calculator gives me 10,056.785. We are talking about people. Does it make sense to say the 10,056.785? Why are you shaking your head no, Riley? Okay, so then what should I change that number to? What should change to a 7? The 6 and 56, so it should be 10,057. And then I want to tell everyone that we're talking about people. Okay, so the next thing I have is a growth factor is the value of 1 plus r simplified. This value can be subtracted instead to give us a decay rate. I want to determine whether each table or function represents an exponential growth function, exponential decay, or neither, and then if it does have a decay or growth, to give the rate of change. So, how do I go from 270 to 90? Okay, I could subtract 180. Do I still subtract 180 to get from 90 to 30? No, what else can I do? Okay, can I divide 90 by 3 to get to 30? And 30 divided by 3 to turn into 10? Okay. So when I have a dividing pattern, this is going to be decay. And that means the growth function is going to be a multiplying pattern. So, this one is what? Decay. And we said it was dividing by 3. I can rewrite that as 1/3. So to find my rate of change, I want to take 1 minus that 1/3. So on the calculator, 1 minus 1/3 gets, oops, I did not type that right. 1 minus 1/3 gets me 0.67. And then I want to times it by 100 to turn back into a percent. So my rate here is a 67% decay rate. Gunter. Okay, so on number 4, what's the pattern there? How do I go from 5 to 10? Okay. Do I go from 10 to 20 by multiplying by 2? And 20 to 40? Okay, so then this one's going to be growth or decay. So then what I want to do is I'm going to take my number and subtract 1 from it to get my percent. So 2 minus 1 is 1. And then I then want to multiply by 100 for my percent. Which gets us 100. Okay. On number 5, it's inside the parentheses. This number is more or less than 1. More, so it's growth. And then to find this percent, I just want to take 1 and subtract it from that value. So 1.07 minus 1 is?
0.07.
And then I want to times that by 100 to get my percent, which is 6. Okay, so what do you think 6 is? Based on that number in the parentheses. Mm-hmm. And then how do I find my decay percent? Mm-hmm. Which gets me 0.02. And then I multiply by 100 to turn it back into a percent, which gets me